All right, welcome to part 2 of our week 5 CAD video here. In the last video, we created this layout sketch and kind of talked about what layout sketches are and how they're used. In this video, we are going to go through some of the process of modeling some of our custom parts. And then next week, we're going to cover the process of importing and kind of finalizing the assembly and doing some things along that line. So I'm going to close this tab up here because I don't need it anymore. I'm going to rename this sketch to layout. And then we're actually going to create a new sketch, but on the same plane. Front plane, create a new sketch. This is where a lot of people differ in the process. Some people will just turn their layout sketch into the first sketch of the first extrusion of their first part or whatever. I usually prefer to keep it separate just because it keeps things a little more organized, and when you're working on more complicated things, that becomes a very critical thing to do. Okay, so basically what we're going to do here is we are going to have 2 plates. One plate is going to kind of cover this entire area, and it's going to provide mounting holes for the motor and stuff like that. And then we're going to have some standoffs. If you remember from earlier in the CAD class, I don't remember what week it was, but earlier in the CAD class we talked about standoffs and spacers and things in our fasteners segment. So we're going to use some standoffs between the 2 plates, and the standoffs are going to space off the second plate, which is not going to provide a motor mounting interface, but it is going to provide bearing supports for the gears. So we're going to start with the first plate, and then we're going to move on to the second plate in a little bit. So the first and most important thing that we need to do is figure out what hole sizes for bearings that we need. So for this bottom bearing, this is really easy. This is just a standard 1/2 inch rounded hex bearing. So that is, I can know that one off the top of my head. That is a 1 1/8 inch hole, or 1.125. You guys should get used to that dimension because the vast majority of bearings used in FRC, and especially on RoboChargers, are this 1.125. So those of you who are students who were students in the 2022 season, you guys probably remember the process of going through and checking bearing fits on the router and everything as we were cutting. So you guys are probably already pretty familiar with this hole size, but this is just kind of the standard bearings. Now this middle shaft up here is a little bit different. It's 3/8 hex. We don't use a lot of 3/8 hex on the RoboChargers. At least we didn't last year. We didn't use any. And so we don't actually really keep these bearings on hand. But so I'm pretty sure it's a 7/8 hole, but I'm going to kind of show you how to check. So we're going to go to vexpro.com. And we're going to go, once this loads, we're going to go up here to hardware, bearings, and then it's going to be Thunder Hex is their rounded hex bearings. They're going to be flanged, and it's going to be this 10.25, which is their 3/8 Thunder Hex. Just quickly look. We don't actually need these. I just wanted to look what the part number is, 5829. So we can... Yes. Okay. I guess I could have just looked. I guess I could have just looked in this list. But the 0.875 OD, that's 7/8. So that's my memory was correct. So what we're going to do is we're going to create a circle that is 0.875. Now, in reality, sometimes it's a good idea to change these numbers. If we wanted to do like a slightly loose fit, this would be 1.126 or 1.127. So you can't always just be guaranteed that you're going to be able to model to the nominal size, because keep in mind, this geometry that we're creating here, this is going to get exported and put on the router and physically cut. So you need to make sure that what you're modeling actually matches the way that it needs to be cut in real life, not just these nominal dimensions that you're kind of just typing in. Now in reality, like bearing fits and stuff, we typically we'll do those in a separate pass, and then we give ourselves the ability to kind of tune the fit. And then once we get a good fit, we just leave those offsets in the program. And so there's a little bit of stuff that happens on the manufacturing side that we have some control over, but in general in CAD, it's important to kind of pay attention to some of the dimensions that you're putting in and not just type them in and assume that your whole fit is going to be good, especially for something like a bearing. Okay, now this up here is not actually a bearing up here where the motor is. If we go to Rev Robotics and we look up the 550 motor and we look at a picture here, you'll see the front of the motor here has this little boss on it that sticks out. The reason that's there is it's supposed to be act as a pilot to kind of that boss is supposed to go into a very precise hole, and it keeps the motor positioned in exactly the right spot in a gearbox. So we basically need to provide clearance for that boss. Now let's go down here to the drawing, and we don't need the web page anymore, and find the dimension for the boss. So it's 13 millimeters. And then generally on these, I want a slightly looser fit than I do on the bearing holes. So the bearing holes, I'm just going to model, to nominal dimension. For the motor boss hole, I'm going to go a little loose. I'm going to go to, I don't know, 13.1 millimeters. Make sure to type in mm, otherwise you'll get 13.1 inches. So that's our hole for our bearing. The other nice thing, if we zoom in, you'll see the kind of the gray lines are from our layout sketch. You'll see that the gear outside diameter is smaller than the hole for the motor pilot. So that means that you can slide the hole, you can put the gear on the motor and then slide all of that through the pilot hole. You don't need to put the gear on the motor after the motor is in the plate, which is a super useful feature in a gearbox. You pretty much always want to make sure that's true. Also, I noticed I didn't really actually address it. I kind of just started going super quick on my screen and wasn't really explaining what I was doing. I'm attaching these circle center points to the center points of the layout sketch, right? As long as the layout sketch is visible, if I hide it, by clicking this little eye over here, it disappears. And these are fully constrained, or you can see they're colored black. But the center points are actually attached to the geometry from the layout sketch, and that's what the layout sketch does, right? It provides a skeleton that we're kind of building our design off of. So I didn't really address that. I just kind of was clicking and forgot to say it when I did it. But that's what we're doing. Right? We're snapping these center points to the layout sketch. Okay, so now comes like a little bit of a less super formulaic part. We kind of just need to decide the outside shape of the gearbox. So I'm going to kind of throw some geometry down. I mentioned in the last video that we want to kind of create our line. When we're doing some more complicated stuff, we want to kind of create our lines and not worry about dimensions and constraints and stuff, and then constrain them after we kind of drop them in. So we want the gearbox to completely hide the gear. There's not exactly a really good reason for that necessarily. However, it looks good aesthetically. It helps keep people's fingers out of different gears, and it keeps it helps keep a little bit of dust and debris out, keeps wires and stuff from falling in there and whatever. And then the other important thing is we need to make sure that there's some material sticking out from the gear so we can like put standoffs in the corners or whatever for that fastening that we need to get. So let's up here above the motor, we really don't need any part of the gearbox to stick up above the motor. There's really no point in doing that. We want to support the full face of the motor generally. That's kind of a piece of advice for designing gearboxes. We don't want to like cut the top of the gearbox off like right here. We want to extend it up to contact the top of the motor. But any material that sticks out from the motor is basically useless. So we're actually going to create an arc. We're going to make the top of the gearbox curve to match the motor. So I'm going to click a drop-down list here. I don't think we've used arcs really in our videos yet, but there's arc tool. And I'm going to create a center point arc. So what you do with the center point arc is you click on the center point and you go outwards, you click the first point, and then I'm not dragging, I'm just moving my mouse. I'm not pressing the mouse button down, and then I click again to place the other endpoint. And so this is not fully constrained. So what we're going to do is click this arc, click this circle, and click a coincident constraint. The size of my icons and stuff are turned up, so I have this drop-down list, whereas you'll still have the full toolbar if you're on a full resolution display. But I increase the size of everything on this on my computer for the purpose of this video, so it's a little more visible on like a phone screen or whatever, right? So now I'm going to create a line and attach this to that, and then attach that to that. I'm going to escape out of that tool. Now we're gonna go through and add some constraints. So I know I want this to be a smooth transition, so I'm going to create a tangent feature between the arc and this line, and then I'm going to again over here click those two, and then I know that I want I know I want this guy and this guy to be kind of like horizontally aligned to each other. I want them to be at the same height, so I'm going to just go ahead and create that constraint, horizontal constraint between that point and that point. And then the other thing that I want is I want this guy and this guy to be equidistant from the center of the center lines of where the gears are, like the shafts. There's a few different ways to do that. The way that I usually do it is I take a line and I find the midpoint of this line down here, which is this like really faint square box. So I click, and then I'll click the center of the gear, and then I'm going to select this and switch this to construction. And then this line just needs to be constrained to be vertical. And then now if I click and drag these lines, they change symmetrically on either side. This is the way that I do it. I like to see this line here. You could create a point and then do a vertical constraint between that point and this. You could create this line not attached to the midpoint and then do a symmetrical constraint. There's a lot of different ways to do it. I prefer to see this dotted line because that visually shows me that this is kind of centered left to right, but that's kind of personal preference there. Okay, so the other thing is any gearbox material that sticks out past this gear is kind of useless, but we just need to make sure that we have room for a standoff in this corner. So we are going to use standoffs that use the 3/8 Thunder Hex profile, and we're just going to kind of assume that they're custom standoffs. There's some Rev products and there's some Vex products and there's some products from McMaster Car and stuff we could use. There's lots of options for standoffs, but we're just going to assume that we use the 3/8 Thunder Hex stock and we just cut it to length ourselves and tap it. Students who are on the team this past season, you guys remember that process. Most of the standoffs we had on our robot were actually made from 3/8 Thunder Hex stock that we just had laying around. There's other things that we can make standoffs out of, and depending on who you are and what team you're on or whatever, like you might make your standoffs differently. So we're gonna just kind of pick that because it's gonna be easy, and then we'll move on from there. So let's just say the edge of the gear and the edge of the gearbox are tangent to each other, right? Because that's kind of the minimum space that we would have available. And let's do the same thing for the bottom. And then let's just make sure a standoff, like if we put a standoff in this area, that it would not hit the gear. So let's go in here and create a circle. Now, once again, the standoffs are a hex, but the same way we did for the hex shaft for this shaft clearance here in the middle, because we're using 3/8 rounded hex profile, the corners are kind of cut on a circular profile, so we can kind of just represent that hex as a circle. So we're going to place the circle down, and that circle diameter is 10.25 millimeters. And then, this guy, we're going to just make it tangent to the edge. Now you can see this circle interferes with this gear outside perimeter. So we can't do this. We have to extend the outside of the gearbox in one direction or the other. So we could make the whole gearbox wider, but I don't really want to do that because that's going to add a whole bunch of material here along the side that I want to avoid. We could make it longer, which adds only material on the bottom. And so what I'm worried about is weight, right? Like I want to do this in the lightest way possible. Now, the other thing we have to do before we make a decision on this, I'm just gonna make this a construction circle, just because I don't actually want it as part of the geometry. And then we're gonna need another set of standoffs up here. Now, we could try to sneak a standoff in here. in which case we definitely have to make the gearbox wider. We also have full control over this geometry still. We haven't decided where this is going to be. So it probably makes sense to put our standoff up here. That's a little bit better too because our motor's right here, and so we're kind of supporting the plate where the motor is. We want that to be a nice rigid mount. If this were a bigger gearbox, I would probably want more than 4 standoffs, but 4 is enough for this because it's pretty small. This line is 3.5 inches long, so this whole thing is really small. So I'm going to go ahead and create another circle up here. Now what I'm going to do, because all the standoffs are the same size, I'm going to switch this to construction. I'm actually going to go ahead and create circles everywhere we're talking about having a standoff. Oops, escape. And I'm going to select these guys, make them construction. And then what I'm going to do is I'm going to select all of these circles, including the one that we dimensioned, and hit an equals constraint. And it will make all those the same size. And so that's super important because now all I have to do is come down here and change this dimension if I want to change what size my standoff is. And so when you're designing something in real life, it is extremely, extremely important. If there's it is extremely important to build out the way that you model things in a way where you are future proofing for changes that you will make, right? So even though like I have already told you we are using 3/8 rounded hex standoffs, this number is not going to change. It doesn't matter. I am not going to put this dimension on each one of these circles because it is fundamentally a better way to design in terms of making things equal and only having one dimension that defines it. Or that is a fundamentally better way to design because later if you needed to change something, you could do it very easily, right? And even though I am defining the standoffs that we're going to use, I'm still modeling this way because I want you guys to get into the practice of doing it that way. That modeling that way is very important, not just in FRC in general, in like in a work environment and everything. Modeling your models in a way where somebody in the future that's not even necessarily you, it could be you in the future and you forgot what you did, or it could be somebody else that doesn't understand your model very well. Making it easy to change things in the future is extremely important. So I'm just going to go through and I'm just going to activate the tangent tool and I'm just going to kind of tangent this guy in place. I'm going to do the same thing up here. I just kind of want this tangent in this corner. So tangent between that line in the circle and then that line in the circle. I'm going to do the same thing over here as well. Tangent between these two sets of lines. Okay. Now, up here, we don't need to worry about this standoff interfering with the motor circle. That's not really something we need to care about too much. That being said, this standoff is going to be kind of like on the front of the plate, like facing towards us on the screen, the way that we're modeling it right now. And then the motor is going to be on the back side of the plate. And so that's kind of an important thing to note. And because the standoff is on the kind of the near side of the plate, that means there's going to be a screw on the back side of the plate. So what we're going to do here is we're going to model another circle that is 0.375 inches, and we're also going to make that construction. It's just slightly smaller than the standoff, but the important thing is this is like a clearance diameter for a button head 1032 screw, which is the screw that we'll be using. In reality, a button head's slightly smaller. It's like 0.361 or something. It's like slightly smaller than this, but I generally just use 3/8 because if you make sure there's 3/8 of space, then you will never have issues. You will never have issues with the screw hitting something. Okay, so what we're going to do here is we just need to make sure that this inner circle does not interfere with the motor, but we don't have to worry about the outer circle. All right, so moving on. So it looks like we don't really have to worry about this standoff clearing this gear too much, but it does look like we need to worry about it here at the bottom like we talked about. So what I'm going to do is I'm going to hover over this bottom line, and there's a bunch of tangent constraints here. So these two tangent constraints over here are the two, you can see I'm highlighting, are the two circles. We don't care about that one. It's this one here. I'm going to left click and then right click and hit delete sketch entity. And now you'll notice a bunch of stuff turn blue, and I can click and drag this bottom guy and move it around now. So what I'm going to do, just what we care about is that there's some gap between here. So I'm just going to go create a dimension between that circle and just define what that gap is. I'm going to do like 0.02 inches, right? That doesn't have to be very much, right? The gears are very precise, the standoffs are very precise. You can have a pretty small gap there. And because we defined, kind of this to be symmetrical and everything, we tangent constrained all of these circles to the edges of the part, like we don't have to do a similar dimension over here, just in one dimension, one place. So let's just go ahead and do the same thing for this upper gear. Let's just do the same gap. It's probably good enough. We could do a different gap if we wanted to, but it's probably okay. And now you'll notice everything's fully constrained. If we wanted a different dimension, like if this screw were still interfering with the motor, we would have to change something about the way that this is laid out. We'd have to make the whole thing wider. We'd have to change what this gap is or whatever. Once everything's fully constrained, like if you're still not happy with it, you have to like make pretty big changes to your sketch. So that's just something to understand, is eventually you will get to the point where it's fully constrained, and sometimes things will still be bad when it's fully constrained, and then you just need to figure out what dimensions you need to change. But in this case, we're pretty good, right? The screw head does not interfere with the motor. It's actually pretty far away. We've got a nice gap between the gear and the standoff, and on the top and the bottom, we've got all our holes in here. We're all good to go. So let us just go over here to the extrusion tool, and it's already kind of selected the right profile, but we're going to make this extrusion 0.25 inches thick, and just like that. Actually, I'm going to make this 0.22. I think we're going to make this gearbox as if it was machined out of polycarbonate, right? Plastic. No reason to make a gearbox like this out of metal. So let's just assume these are polycarb plates, in which case the polycarb that we have that's quote unquote a 1/4 inch thick is actually 0.22 inches roughly. So we're going to do that. Now you'll notice there's no holes for the standoffs. That is intentional. You should not, creating holes for bearings in a sketch like that is fine. Creating bolt holes in a sketch is bad, because like we mentioned last week or the week before, there is this whole feature that is specifically meant for creating bolt holes, and it gives you a lot more control, and it captures more design intent rather than just having a bunch of circles in a sketch. So do not put bolt holes in your sketches. That is a very bad thing to do. It is confusing to people that edit your part in the future, and it's just generally a bad practice. People will get upset with you if you do it. So we're going to kind of add those holes later. But before we do that, let's kind of figure out how we're going to bolt this motor on. We need some screws for this motor as well. Okay, so there's a few different ways to do this. So we could put this in the sketch, and honestly, a lot of times I would put it in the sketch, like the layout sketch, I should say, is like where the bolt holes will go, or kind of like what diameter the screws need to line up, because that's kind of an important piece of information. In a situation like this with a gearbox like this, I just find it easier to leave it out, but it doesn't really matter. So we've still got the drawing open up here. Let's kind of look at this. So these are M3 tapped holes in the front face of the motor. There's 4 of them, and they lie on a 25 millimeter bolt circle. So we just need to provide some places to put M3 screws on the face of our gearbox plate on this bolt circle, and we'll be good to go. So there are some feature scripts that help with this. I don't really want to use them for this right now, because I kind of want to show the process of doing it manually. However, there are some shortcuts to adding motor mounting patterns that if you want to play with yourself, you can. I think we added it. If I look here, yeah, it's this motor mounting one. If you want to play with this, you can. We will use this later in the class. I will kind of demonstrate how it's used, but for now, we're just going to kind of do it manually. So what we need to do is we need to create a sketch on the front face of this thing. And actually, I'm going to hide our layout sketch because we're basically done with it at this point. I'm going to create a sketch here, and what we need to do is we need to sketch that 25mm bolt circle. So I want to attach to the, if I exit out of this and I reactivate the circle tool, um, you kind of just need to kind of bring this circle to attention, and then once you kind of hover over it and it highlights, then you can go to the middle and select the center point. It's kind of a weird, like, kind of tactile, like, little trick that it's easy to do if you know what you're doing, but if you're new to sketches and you're not familiar with some of these kind of idiosyncrasies, you'll you'll like get frustrated of why it's not letting you snap to the center point of the circle. So that's just something to be aware of. Is like you got to hover over the thing first to kind of bring it to Onshape's attention, and then you have access to the center point. So we're gonna type in 25mm, and then I'm gonna switch this to construction. So now, really, we only need to mount the motor with 2 screws. However, we're gonna put all 4 in there, just to kind of, you know, give us some options. The motor has wires sticking out of it, and typically when you're doing the mechanical design of a robot, you don't necessarily have a super firm kind of plan for exactly how the wiring is going to be routed, and so it's important with especially motors to give several different orientations that you can mount the motor in, so that the wires can stick out in different directions depending on how you decide to wire the final robot. So we're going to go ahead and put just 4 mounting configurations in, or 4 mounting holes in, and then because the holes are all 90-degree apart, that means you can clock the motor at 90-degree increments. You could do more than that, although at some point it becomes kind of onerous to manufacture, a lot of holes in this kind of crazy pattern or whatever. But so we're going to put 4 holes in. Now, what I'm going to actually do is I'm going to rotate this pattern 45 degrees because the wires come out at an angle, and I'd like, in general, I'd probably want to plan on the wires coming out the side or maybe just straight out the top, depending on how this gearbox is used in a robot. In our case, this is not actually getting used in a robot. This is just an example design that we're doing just for the sake of the gearbox. I just want to give a couple different options that are a little bit nicer for the wire orientation. So we're gonna rotate this whole pattern kind of 45 degrees. So a little trick that I like to do is I'll just, when I'm creating a 4-hole pattern like that, I will just create a square, and I will attach one endpoint to the circle, another endpoint to the circle, and then this is kind of freaking out on me, so I click this other point and snap it to the circle as well, and then that gives me this kind of shape here. And then what I'll do is I'll select 2 edges, I'll just make them equal, and that's just how I get 4 points that are equidistant. That's just a little trick that I like to do. There might be easier ways to do it. Some people will do crossing lines or different things. So that's just how I do it. Once we've done this, we're going to use these corner points for the hole feature. So we don't actually need to do anything more here in the sketch. We can just finish it. And then let's click the hole feature. And these are going to be simple holes. They're going to be through holes. They are going to be ISO standard because they're metric. They are going to be clearance. The size is going to be M3. And we will do a close fit. Got to be, actually no. We've got this pilot here, and that's constraining the motor boss. So we'll do a normal fit. So there's a little bit more slop. Another thing to pay attention to here when you're doing these small hole sizes, specifically for RoboChargers, when we cut stuff on our router or on our gantry mill, we use an 1/8 inch bit. So you can never have a hole that's smaller than 1/8 inch. There's some things that we can do, like we want to swap out a tool and do some small hole, we can, but generally speaking, if at all possible, we avoid doing any features that are smaller than 1/8 inch because that allows us to just cut the whole part with an 1/8 inch bit, which is super easy. So then from here, we just need to select our sketch points, where to place the hole center points. Select those 4 points. The merge scope is the only part that we have, so that's fine. Okay, so that's the motor mounting interface. That's good to go. The one thing that we're going to have to worry about a little bit when we get into the assembly of this is just to make sure that any screw heads that are sticking out here don't interfere with our gears, right? We could, actually, now that I'm thinking about it, I kind of want to reorient this whole pattern, actually. Yeah, I'm actually going to do it. So we're going to go ahead and make a change. So What we're going to do here is I'm actually going to turn this whole pattern back 45 degrees just to kind of match what we see on our screen here. The wires won't come out at quite as nice of an angle. They'll come out here at a weird angle or down at an angle, but that'll be okay. The advantage to that is that the holes will be like here and here, and that means the screw heads will not interfere with the gear at all. And that means that I can take the motor on and off without needing to worry about the the gearbox, like the gear being in my way of getting to the screws. I don't have to take the gearbox apart, just take the motor off. So it's a generally good practice to make sure that you can get to the screws without them being hidden by the gear. So let's go back and edit our sketch here. Oops, I think I just hit copy sketch. Let's go edit. And then we can just rotate this square. We just need to find which one of these. One of these has a vertical constraint on it. I believe it's the bottom one. Oh, bottom one has a horizontal constraint. So we just right click, delete that, and then we can just rotate the square. And then I'll just do a vertical constraint from this corner to that hole there. That's probably the best way to do it. Okay, so then we exit out of that and our whole pattern is updated. And then because there's 4 holes on the motor and there's 4 holes here on the plate, we can use any 2 holes in any orientation. And then in reality, probably what we will do is just always use this hole and this hole. The top and bottom ones are less useful because, one of them is hidden by the gear. So we could just place these 2 holes, but I generally like to put the extra holes in anyways, just in case. Okay, so let's also just double check here real quick. At this point, usually I would just kind of eyeball this and be like, yeah, this is plenty big enough for a screw, but let's just make sure that this is big enough and the screw would not hit the gear. So let's just edit this sketch, and we're gonna use the rev hex head screws. We could use button heads or socket heads, and it doesn't really matter. But I think we're going to use the Rev hex head ones because those are the ones that we use for FTC, and we've got like a bunch of them in the shop. So if we were building this in reality, we would actually use those screws probably. So that is a 5.5 millimeter hex. So I'm going to go up here, create this Inscribed Polygon tool. Actually, I take it back. I want the circumscribed polygon. Click this. Now it defaults to a hexagon, so what you need to do here is if you click and then you move your mouse, it'll increase or decrease the number of sides, which is a little annoying. So you got to if you want a hexagon, you just need to click to the center point, click, and then click again without moving your mouse, just to kind of make sure that it stays on 6. Otherwise, it'll change the number of sides, which is annoying. Okay, so I needed to dimension this hex size, so I'm going to do a dimension here between the flats. It's 5.5 millimeters. That's just the size of the hex. And then it should lock the orientation automatically because it puts in a horizontal constraint to keep it. But sometimes if you put it in at a weird angle, it'll be constrained. You'll have to put like a horizontal constraint or a vertical constraint on one of the edges just to keep it from rotating. Now the nice thing is, and this is the reason I did the circumscribed one, is it comes with this construction circle. So regardless of what orientation the screw is in, because obviously the screw can spin, so the corners could be anywhere along this circle. So this circle is kind of like the keep out area for this screw. So if we click on our layout sketch here, actually let's exit this sketch. And that geometry doesn't affect our whole pattern, it's just kind of in there. So if we click on this click on this sketch and click on the layout sketch, they both highlight, and you can see that the screw's nowhere close to the gear, so we're fine. So eyeballing it was good enough, but that's how you would actually check if you had a screw that was really close to something. Okay, so we've got a little bit to go here. All right, so now we need to create a second plate. Now there's a little bit of special geometry that's going to go on here. I'm not going to explain exactly how we're going to do it right now. I'm just going to kind of talk you through what to do, and then we are actually going to address that next week. So what we're going to do is we're going to create a plane. We're going to create a plane that's offset from this surface of this plate. So we're going to select that surface, click plane, make sure we're on the offset option, and we're going to do like, I don't know, 0.75 or something. That dimension is definitely wrong, but we'll come back and fix it later. Click OK. OK. Hide that plane, and then I'm going to select it and then create a sketch on that plane. Now what we want to do is we want to create the geometry for this second plate that we're going to have. So there is this tool that's called use or project or convert, and it basically allows you to pull geometry in from either another sketch or from some model geometry that's actually in your part studio. So what we're going to do is we're going to select this hole and this hole. These are our bearing holes, and we need these bearing holes to also be in the front plate of the gearbox. So we're going to select those, then we're going to hit use, and you'll see it projected them. It projected them outwards onto our sketch plane, right? Because we're making a sketch kind of way out here floating in the air. So now we've got these circles. The other thing we're going to do is we're going to make our sketch one visible, and we actually need the circles for the standoffs up here at the top. We don't actually need the bottom ones because the bottom of the gearbox plates are going to be the same, so we're going to just leave those alone. But we're going to project these top ones, and then I'm going to go back and hide this sketch again just so it's not annoying. So then what's going to happen here is we're going to have a rectangle that comes up. It's the same size as it is here on the bottom of the gearbox, and then it just needs to go right across the top of this standoff here. And now that I'm actually looking at this, no, we'll address that later. Okay, so I'm just going to create a rectangle that just kind of loosely hugs all this. It's going to be tangent there between those two, and then I'm just going to do coincident constraints between the other edges. I'm hitting escape like right now, and then select the two, and then coincident, and then hit escape again, right? That's how I'm doing all those. But you can also click the constraint tool and click each thing that you want to constrain. So now in reality, I want to be able to get a tool in here to get to this screw. I don't actually know the diameter of the nut driver that we use for these screws. I'm just going to go in and create a circle. I guess I have to actually project these. I'm actually gonna do it based on the sketch. I'm gonna just select these 2 points and hit use. I think it's better to use the sketch geometry. It's kind of a wash. If I go back and delete stuff and move stuff around, it's gonna break. It's gonna create errors in the future anyways. So create a circle there, create a circle there. I'm gonna select both of these, make them equal to each other in size, and then I am going to attach a dimension to this and make this. Oh, I don't know. Actually, you know what we're gonna do? Actually, I take this back. Wonder how big. I'm going to try something. I'm going to delete this dimension. I'm going to create tangent that to that. No, that's too big. All right, let's just do like ½ an inch. Oh, that's almost the same size. I think that's okay. And then so basically what we're going to do is we're just going to kind of notch out the edge of the plate. I'm going to make this a little smaller, like that. The nut driver is definitely not that big. It's pretty small. And then basically we're going to have these corners going to get radiused, so don't worry about that. But we're going to kind of notch these out to provide clearance for our nut drivers. But then this little stick up area in the middle here is kind of useless. It's not adding any strength. It's just adding weight. So I'm just going to add a horizontal line here. It'll snap to horizontal. I'm going to select these two and make those tangent. And then we'll just remove all that material there. Okay, so we should be good to extrude this now. And then it's kind of selecting everything, but we don't want to extrude everything. We're going to close out we're going to click that little X and get rid of that. We would just want to do this region. And then this one's also going to be 0.22. So let's select that. And then it's on new, which is fine. There's something intersecting. It wouldn't automatically switch to add, but just make sure it's on new. And click OK. Okay, so now what we want to do, now that we've got both plates, we want to add the screw holes. Now we already did in sketch one, we already did put where the standoffs are going to be. So if we just make that sketch visible like I just did, we can just create the screw holes using that sketch. So we just go to the whole feature. Simple and through is fine, but we need to go back to ANSI. Clearance, yes. Number 10. And this is going to be a close fit. And then sketch points, select these 4. And then the merge scope, we just want to make sure that the merge scope is both parts because the holes need to go through both parts. So click OK. All right, so those are our screw holes. Now what we're going to do is we are going to use, I guess we are ready for the standoffs at this point. So let's use a feature. So we're actually going to use a feature. It's called the shaft generator. The shaft generator is actually made for doing shafts, as you would probably expect from the name. However, it is actually useful for creating standoffs as well because they're kind of the same process, and I'll kind of explain why that is. So let's click on that. This is a custom feature script for FRC. If you guys don't have this, you should go back to our week 1 CAD videos and go through the process of adding these. Okay, so our shaft type here is going to be 3/8 Thunder Hex. This is one of the reasons why we're using the shaft generator, because it already has 3/8 Thunder Hex in there, and we're using 3/8 Thunder Hex shaft stock as our standoffs usually. The important thing here is we're not using a shaft collar, we're using a bolt and washer. Basically, obviously this is all built for shafts, so it's kind of a little bit weird, but bolt washer basically just means the ends of the shaft are tapped. There's a threaded hole in the end, either end of the shaft. That's the way that the RoboChargers usually do our shafts. We don't usually use snap rings or shaft collars or anything. And it just happens that this works for making standoffs. This drop down here should be up to face. And then down here in this origin box, we're going to pick one of the holes. Now we only need to model one standoff in one location. I'm actually going to do it down here in this corner. We only need to model one standoff in one location, and then we will just place additional copies of that standoff in other locations. So once we pick this circle for the origin of the standoff, and then we're going to go up here to end face, and we're going to pick the inside face of this gearbox. You'll see this kind of like ghost thing shows up. And then we can just click OK, and now we've got our standoff. Okay, so at this point, let's do a few things. Let's set materials. So for part 1 and part 2, we right-click and we hit Assign Material. These are going to be polycarbonate. And actually, if we right-click and hit Edit Appearance, I usually use this color for polycarbonate. It's this kind of off-white color. Now, polycarbonate is actually transparent, but it's really annoying to look at transparent parts and kind of try to click on stuff with transparency all over the place in your model. So when I'm working on design, I usually use this color for polycarbonate, but then when I'm done, I then go back and set it to some transparent color to make it look nice in the model. So we're going to do that for now. The 3/8 Thunder Hex, if we edit the material, it comes with its own custom material. The feature script sets its own custom material. You could switch it to be the built-in 7075 one, or you can just use the custom one, doesn't matter. The one thing I will do is edit the appearance. Oops, that's not what I meant to click. Right-click, edit appearance, set it to this darkest gray. I don't like to use the actual black one because it's too dark and you can't see it anymore. So this gray is good. And then the only other thing to do is we're gonna round the corners. You want to make sure the corner rounding is kind of the last thing that you do. We are also probably going to add a lightning pattern to this in the next video. I'm not going to show this this week because there's some other stuff that we need to do. But we're going to go ahead and round the corners now. Typically, I do all of my important geometry, and then I do corner rounding, and then I do lightning. I usually do lightning after I do corner rounding. It helps avoid some issues in a few different situations. So I'm just going to use the fillet all edges feature, and I don't know if I can do two? I can do two. Okay. And an eighth of an inch round is fine. You know, it looks pretty good. It's kind of arbitrary, aesthetic. Just doing fractional numbers is fine. Okay, so those are our parts. There's still some more work that we need to do on the modeling thing to get this gap correct, and then, like I said, lightning features. But we can't figure that stuff out until we get more of the assembly built. So I'm going to go down here to the assembly. We're going to just do a little bit of the assembly this week, and then we're going to do a lot more next week. So we're going to go over to the assembly. Normally, I would like to rename these things. RoboChargers, we have a part numbering system, but I don't want to make the CAD class about that. So I'm not renaming anything, but generally speaking, do not leave parts as their default names over here. That is very confusing in the future because you're going to have a bunch of part studios and they're all going to have a bunch of part ones in them, and it's just bad. I'm not doing it for the CAD class just to save time and not distract from the important content, but don't leave things their default name, right? In fact, we're going to rename the assembly. Yep. Okay. All right. So in the assembly, we're going to go to Insert. We want to make sure we're on Current Document. Now, there's nothing in this assembly, and we actually want all of the parts from the Part Studio in here. So we can just click on the Part Studio, and it'll just place them all. And then we're not going to click in the viewport anywhere. We're just going to click this green check mark. Now, the thing to understand is that these are not positioned anywhere. So like we talked about in the assembly video, if I click and drag on any of these, they'll move out of place. So I'm going to undo that. Now what I want to do is I want to go to the group feature and group these three parts. That will basically force them to stay in the same relationship to each other as they are in the Part Studio, which is exactly what we want. We modeled them in the correct positions in the Part Studio, so we don't need to worry about what position they're in here in the assembly. We just want them to be the same position they are in the Part Studio, except in the assembly. So we group them all together to make sure they stay in relation to each other. Now there's one last thing we have to do, because now they just all move together when we move them, so I'm going to undo that. And then we actually just need to pick one part. We'll pick this main plate here, right click and hit fix. Okay, now nothing will move. Okay, so then that's great. Now the other thing we're going to do is we're just going to select the standoff. I'm going to hit Control C on my keyboard to copy it to the clipboard. Click up here and Control V and Control V and Control V. We're going to just paste a few more. Now what we're going to do is we're going to go create a fastened mate. We're going to click that circle, and we're going to constrain it probably to the base plate here like that. Go back, constrain this one, click, and whoops, click, didn't go, click, there we go. And then click there, come on, there we go. Okay, so now we've got 4 standoffs in here. Now, like I said, the spacing in this gearbox is not correct. But next week, once we get some of the other components in here, we will correct that spacing. And because we built this all in the Part Studio, the standoff lengths will change and everything will just update. So we are going to stop there for this week. Next week, we're going to come back and we're going to add all the internals. We're going to add the motor. We're going to model shafts. We're going to model. We're going to put the screws in there. We're going to finish this all up, and then we're going to end up doing the lightning pattern as well. So thank you guys for watching. Stay tuned. Work on this week. Make sure that you guys follow along with this video and the last one. Make sure you guys get your model to the same point that I've gotten mine here. And then next week we'll have another set of videos finishing this up, and you guys will have a complete gearbox at the end of it to show for it. So thanks for watching. I will see you guys next week.